Right. Hello everyone. I thought I would show you how to do the homework questions just in case the mark scheme was a bit too hard to understand, or you kind of lost track of the steps at some point looking at the mark scheme. So I thought I would just show you how I think when I'm trying to do this question. So the first thing, so it's all about reading the question slowly, carefully, taking each of those keywords and then trying to translate them into their implications. So the first one that you see, a uniform rod. So whenever you see the word uniform rod, I'm going to draw a rod. So that is AB, and in the middle I'm going to put the entire mass. So I will search what is the mass. So the entire length is 1.5, so I'm going to divide that into two equal halves. This is going to be 0.75, this is also going to be 0.75, and the entire mass is 8 kgs, so I have a force of 8 g's acting downward. So always remember, whatever is the mass, you times that with the g force or the gravity, that will give you the force that is acting downwards. A particle of mass m kgs is attached to the rod at the end B. So I'm going to take a particle, and the mass of the particle is m kgs, so that is going to apply a force of m times g. So mg is the force that is acting downwards. The rod is supported at the point C. So there's my support, which is the point C. So if you look at the picture now, A to C is 0.9. So A to C is supposed to be 0.9, and we know that this much is 0.75, so the remaining part is supposed to be 0.15. So if that is 0.15, I can now take off this one and say this is 0.6. Right. It says the system is in equilibrium, so whenever you see equilibrium, that means all the forces that are going up are equal to all the forces that are going down. All the clockwise moments would be equal to all the anti-clockwise moments. I'm sorry, I have a running nose. Show that m is equal to 2. So the first thing that we can do is we can take the reaction force. So whenever you draw a support, always remember there is a reaction force that is going to the top as well. But that reaction force, well, does it really help us? Okay, yeah, let's see. So what we are going to do is we are going to take moments. Now the question is, where do we take the moments about? Should I take the moments here? I want you to think for a moment, see if that would be a right point. Now, if you thought no, then you are right. The problem is, if I take the moment here, the force mg would be actually going through my pivot point, and that would make that entire moment go 0. So I would lose this mg to the 0, and I will never be really able to figure out what is m. So except B, we can take the moment about any other point. So you can choose A, you can choose this point, you can choose C, whichever point you like, you can choose that. So I'm going to take C for this question. So taking moments about C. Why am I doing C? So that I don't have to worry about the reaction force, so that itself is gone. So I don't have to worry about what is R, because if I go for R, then that's even more complicated. So I want to skip what is R, so I'm going to lose the R. So taking moments about C, we will now have, so there are only two forces now. One is the 8 G's that is acting in the counterclockwise direction or the anti-clockwise direction. You have mg that is acting in the clockwise direction. So we can now go 8g, which is my force. Now my pivot point is C, So I'm going to make that a bit bigger so that we can figure out what is the perpendicular distance. So 8g is my force. The perpendicular distance is 0.15. So 8g times 0.15 should be equal to, so this was in the anti-clockwise direction. So in the clockwise direction, you've got mg, which is my force, and the perpendicular distance to the point is 0.6. So you now have mg times 0.6 that is acting in the anti-clockwise, in the clockwise direction. So both of these should be equal, and then all we have to do now is solve for x. So g and the g goes off, and you have m is equal to 8 times 0.15 divided by 0.6. So 8 times 0.15 divided by 0.6, and that is 2. So that is the first question, which is 2. So things that I want you to remember, or easy things to remember, because I have the reaction force here, if I try to take, the moment about any other point, it kind of makes things more complicated, but because then you will have a simultaneous equation and blah blah blah. So I wouldn't go for that. I would just try to get rid of that r, because I don't want r in the first place. I want only m. So I am taking the moments about c, so that r times 0, because the line of force is inside or in line with my pivot point, that kind of cancels off, giving me m is equal to 2. So that is part A. Right, so for part B, a particle of mass 5 kgs is now attached to the rod at A. So it's pretty much the same diagram, but now you have at A a particle of mass 5 kgs. So that means the reaction force that is going down is 5 g's. We had figured out that at B you had 2 kilograms, the m mass was 2, that means the force that is going down is 2 g's. It is still the uniform rod, meaning in the middle you have 8 g's. So this is 0.75, this is also 0.75. The point, is attached to the rod at A, and the support is now moved to from C to a point D. So from C, we're going to move it to a new point, which is D. We don't know where D is, but I guess we'll find out. Yeah. The system, including both particles, is again in equilibrium, so all the forces that are going up would be equal to all the forces that are going down. So the forces that are going up, that is my reaction force, and we have to find the distance AD. So we have to find this distance. So you can either call that entire distance as x, or what we can do is we can call this distance as x. So from the center of the rod to the point D, you can call that as x. If that is x, now a mistake that I made, if you leave your picture like that, you might be tempted to think this is 0.5, but no, we know that the half is 0.75, meaning the remaining distance would now be 0.75 minus x. So make sure that you are getting the lengths right on your diagram. Once you get that right, then this should be a breeze. So we have to find what is x. Now ideally, I don't want to have two unknowns, so the best thing that I would do, get rid of this reaction force. So I'm going to take moments about the point D. So taking moments about the point D. So the first force that we have, that would be the force at A, which is 5 g's, and it is going down or going in the anti-clockwise direction. So 5 g's, that is my force. The perpendicular distance towards the pivot point, that is 0.75 plus x. So I have 5g's times 0.75 plus x, and that is going in the anti-clockwise direction. The next force is 8g's. That is also going in the anti-clockwise direction. So this is plus 8g's times x. Now on the other side, the other force that I have is 2g's, and that is going in the clockwise direction. Perpendicular distance is 0.75 minus x. So I now have 2g times 0.75 minus x. So now 5g's times 0.75 plus 5gx plus 8gx. So this will now become 13gx. 5g times 0.75 equals 2g times 0.75 minus 2gx. So 5g times 0.75, 2g times 0.75, that will become minus 3g times 0.75, and then the minus 2gx, okay, maybe I'll just write one more step, minus 2gx, then I can say the minus 2gx and the 13gx, that becomes 15gx, so, you know, adding the 2gx on both sides, equals minus 3g times 0.75. We can cancel out the g and the g, so that goes off. And then 3 and the 15, that becomes 5. So I can say x is equal to minus 0.75 divided by 5. So that is minus 0.15. So the little distance, or the little x that I have, that is minus 0.15, which means the distance AD will now be equal to, so AD will now be equal to 0.75 minus 1.5, which is equal to 0.6 meters. And that is part